Good morning and welcome to the 2017 AP Chemistry FRQ walkthrough for question 6. Question 6 starts by saying, answer the following questions about magnesium hydroxide. At 25 degrees Celsius, the value of the solubility product constant, or KSP, for magnesium hydroxide is 1.8 times 10 to the negative 11th. A then goes on to say, or ask, calculate the number of grams of magnesium hydroxide molar mass, 58.32 grams per mole, that is dissolved in 100 milliliters of saturated solution of magnesium hydroxide at 25 degrees Celsius. All right, so we want to know how many grams we have in 100 milliliters. So this seems like it's a pretty simple unit conversion problem. So let's just start there. 100 milliliters of solution. And, well, crud. I don't know where to go from here. I need to get from milliliters to grams. Now, typically I could use like molarity to go from milliliters to liters to moles, and then use the molar mass to go from moles to grams. But I don't have that option because I don't have the molarity. But I do have the option to find the molarity. So let's go ahead and do that. The process for dissolving the magnesium hydroxide in water would be this. And if I write the KSP expression for this, I'll get KSP equals the concentration of magnesium 2 plus and the concentration of hydroxide squared. Okay, let's keep going. We know our KSP, so all we need to do is solve for concentrations. If you want, you can go through an ice table, but it's simpler to go, okay, for every 1 magnesium hydroxide, we get X amount of magnesium and 2X, because there's a 2 hydroxide. So in this case, equals X times 2X squared. And from here, all we need to do is solve for our X using our KSP, which is the 1.8 times 10 to the negative 11th we have up there. Follow your order of operations, square this, and then multiply by X. You'll get 4x cubed equals 1.8 times 10 to the negative 11th. Divide the 4 to the other side, then take the cube root, and you'll get x equals 1.65 times 10 to the negative 4th molar. In other words, that is how much magnesium you have, or magnesium ion you have, which is also the same amount as the concentration of the magnesium hydroxide. So your concentration of Mg equals your concentration of magnesium hydroxide, which is equal to this number here. So now we can do our conversion. We have 100 milliliters using our molarity. We know it is 1.65 times 10 to the negative 4th mole per 1,000 milliliters of solution. and that's moles of magnesium hydroxide. And now we can use our molar mass to go, well, 1 mole of magnesium hydroxide is 58.32 grams coming from right here. Multiply that out, and you should get 9.6 times 10 to the negative 4th grams of magnesium hydroxide. This problem's worth 2 points. 1 for finding the correct solubility down here, and 1 for finding the number of grams. That's it. In general, when you have one of these problems and you're not sure where to start, I generally try to set up a conversion table or an equation and go, okay, if I had this piece of information, I could solve this. Now, how do I find that piece of information? That's exactly what I ended up doing here. B continues on. It says the energy required to separate the ions in the magnesium hydroxide crystal lattice into individual Mg2 plus gas, OH minus gas ions, as represented in the table known as the lattice energy of magnesium hydroxide solid. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. Okay. There's a lot going on here, and typically you don't talk about lattice energy until you're a little higher in chemistry classes. But we know about Coulomb's law, and we do know about periodic trends. So let's break this down. What this sentence, this paragraph here is telling us is that lattice energy is a representation of the amount of energy you need to put in to break the magnesium hydroxide into magnesium and hydroxide. So you overcome the forces or attraction keeping them together. The attraction between the magnesium and the hydroxide is given to us by Coulomb's law. Coulomb's law is replicated here. It says the force between two particles is equal to a constant times their charges, so in this case 2 and 1, divided by the distance between them, squared. So if one of these has a lower force than the other, either it has to have higher charges or a lower distance. So let's take a look at this. Magnesium hydroxide into magnesium and hydroxide, Mg2 plus, OH minus. Strontium hydroxide into Sr2 plus, OH minus. So it can't be the charges, so now we need to look at the radius. If we go look at our periodic table, I've got a mini one just with the relevant data kind of encapsulated here. I notice that magnesium is above strontium. Strontium is 2 down from it, right here. Which tells me that strontium is going to have a larger radius. How do I know this? Well, it's farther down the periodic table, which means it has more orbitals of electrons, which will give it which will require it to take up more space. Alternatively, you can say periodic trend is that molecules get smaller the farther down and to the left you go. If you go down from magnesium, you reach strontium. So, putting those two pieces together, first things first, we can absolutely say that the strontium ion is bigger than the magnesium ion because it has additional occupied energy levels, or it's farther down the periodic table, or shells, take your pick. From that, we can say, according to Coulomb's law, because there's a larger distance between the nuclei of the strontium and hydroxide, the force between them will be smaller, because when you divide by a larger number, you get a smaller number. 5 divided by 1 gives you 5. 5 divided by 5 gives you 1. 5 divided by 10 gives you a half. The bigger the number you divide by, the smaller your answer. Coulomb's law will then tell us that, because if you divide by a larger number, it gives you that answer. Therefore, the attractive forces between the strontium and the hydroxide are smaller. than the ones between the magnesium and the hydroxide, thus giving it a lower lattice energy. This is again worth 2 points. One for the correct comparison of the cations. So comparing the size between this and this, which comes from here. And one for giving a justification based on the larger distances gives a smaller force, or a smaller distance gives a larger force, giving you the difference in lattice energies. The full answer, according to the AP guide, is the strontium 2+ ion is larger than the magnesium 2+ ion because it has additional occupied energy levels, or shells. Coulomb's law states that the force of attraction between a cation and an anion is inversely proportional to the square of the distance between them. Since the distance between magnesium 2+ and hydroxide is shorter than the distance between Sr2+ and OH-, the attractive forces in magnesium hydroxide are stronger, and therefore its lattice energy is greater. Seems like a lot, but ultimately what you're asking about is, what are periodic trends? How do those work? Coulomb's law. Do remember this, it is not an equation given to you, and thus you'll need to know it, especially because there's always a question about Coulomb's law. And that is 2017 AP Chemistry FRQ number 6.